So we have been given a graph. On the y-axis, it is momentum. On the x-axis, we have time. We need to figure out what is the net force acting on the object for the first 2 seconds and for the next 2 seconds of the motion. So how do we approach such questions? So remember, in physics, whenever we have graph-based questions, there are only two ways in which you can proceed. Either you find the gradient of the graph or area under the graph. But how do you select which approach to pursue? So for that, let us quickly revise the concepts. So remember, does not matter whatever the graph kind be, there will be axis, right? So y-axis and x-axis. If you have to figure out the gradient, that is y-axis divided by x-axis. To be specific, it is actually delta y by delta x. But just for solving questions, just remember the shortcut. Gradient is y-axis divided by x-axis. And the area under the curve will be the product of the axis, y-axis in multiplied by x-axis. Now let's go back to the question. Y-axis is momentum p, x-axis is time. So the gradient will be p upon t and the area under the graph will be p into t. Now which one do we take, gradient or the area? That will be dependent on, do we have a formula which connects the momentum with time? If you think about it, yes, we have the formula. So the formula goes like the impulse momentum theorem, if you remember, force can be written as change in momentum upon time. So rate of change of momentum is force. And in the graph which is given to us in the question, momentum is the y-axis, time is the x-axis. This is gradient, which means that the gradient of the graph which is given to us will give you the value of force. So let's go back to the graph. Initially, okay, the coordinates are 0 comma 0. Then this particular point we can write as 2 comma 20. So all you need to do is, if you can figure out the gradient of this line, that will give you the value of force. So let's write down. For the first 2 seconds, gradient will be, we'll use the formula y2 minus y1 divided by x2 minus x1. So we'll write 20 minus 0 divided by 2 minus 0, which simplified, we'll get 10. So 10 Newton is the force for the first 2 seconds. Hence, option B and D can be eliminated. After 2 seconds, if you notice, the graph is a horizontal straight line and the gradient for horizontal straight lines are 0. Hence, we can say force for the second 2 seconds is equal to 0. Hence, A is the right answer for this question. So here it is mentioned that a ball of mass m collides with a vertical wall with initial horizontal speed u and rebounds with a horizontal speed v. And then they have shown the graph of speed versus time. So you can clearly see that before the collision, the initial speed was u. After the collision, the speed was v. But during the collision, this transition happened from u to v. So the question is, find the magnitude of the mean net force of the ball during the collision. Now, before you even solve this question, it is important for us to understand which force is being talked about. And this is the keyword which we need to be careful of, during the collision. So which is that force acting on the ball during the collision? So let's see. So we have a ball which is about to hit a wall with initial speed u. This happens before the collision. So the ball is going to hit the wall and rebound back. So after the collision, the ball has to go towards the left side with, let's say, a speed of v. So this is before the collision and after the collision. But there is a transition period in the middle, which is called during the collision. That's the point where the ball actually makes an impact with the wall. Now, since the ball was traveling rightwards and it hit the wall towards the right, hence the wall is going to experience a force. So that force is provided by the ball but applied on the wall. Now, according to the Newton's third law, every force is in pairs. That means the wall is also going to push the ball towards the left hand side. Hence, this force represents the force which is provided by the wall but applied on the ball towards the left hand side. And it is this force which the question wants us to find. And how do we get this value of force? Using the impulse momentum theorem, which is J is equal to F delta T, which is equal to delta P. Since we need to figure out the value of the force, let's make force as the subject. We will write F is equal to delta P divided by delta T. Now, delta P is the change in momentum. So let's write down final momentum minus initial momentum divided by time taken. But please note this delta t is the time taken during the collision. And how do we figure out the time of the collision? So from the graph, you can see, let me label some points. So let's say A. A is that point just before the collision. And then if I label point B, this is just after the collision. So what is the time taken between A and B? This will be T2 minus T1. And that we need to put in the denominator. So delta T will be equal to T2 minus T1. Now, momentum is mass into velocities. Let us write down the final momentum should be equal to m into the final velocity, which is v. But this is where we need to be careful. As we know, momentum is a vector quantity, so we need to be careful about the direction of those velocities. Let me show you the diagram again. So, before the collision, the speed was going rightward, so that u will be positive. After the collision, the speed is going leftward, so which means this v will have to be taken with a minus sign. So final momentum should be negative m into v. And initial momentum will be just m into u because that u is anyways positive. So let's put these values in the formula for force. So let's write down force will be equal to the final momentum is negative mv. Initial momentum is mu divided by time taken is T2 minus T1. Now let us go back to the options and check, does this fall under any of the options? Also, please look at the keyword in the question. We have to find the magnitude only. So we need to take out all negatives out. So how do we do that? Let us try to make negative m as common in the numerator. So here we go. So let's write down f will be equal to negative m will be common, and what should I write in the bracket? It will be V plus U. V plus U. And in the denominator, we will write T2 minus T1. And now let us look at the options. So M into U plus V by T2 minus T1. So we can ignore the minus sign. So the answer is actually option D. M times U plus V divided by T2 minus T1. So this is a very interesting question. It's mentioned an astronaut is moving at a constant velocity in the absence of gravitational field when he throws a tool away from him. What is the effect of throwing the tool on the total kinetic energy and the total momentum of the astronaut and the tool? So before we get to the kinetic energy, let's focus on total momentum because that is easier. If we recall the law of conservation of momentum, which states that for a system of isolated bodies, the total momentum is always the same. So initial momentum and final momentum, they are always equal. And if we go back to the options, it is asking total momentum of the astronaut and the tool. Can it increase? No, because then it will violate the law of conservation of momentum. Initial momentum and final momentum are supposed to be equal. So there should be no change. Hence, we can eliminate option A as well as option C as total momentum cannot change. Now, what about kinetic energy? This is where it gets a little tricky. So let's read the question again. An astronaut was moving at a constant velocity. So let's draw a diagram. Imagine we have an astronaut, and just for the sake of simplicity, let us take a value of 1 kg. So 1 kilogram astronaut. It is traveling with a speed of, let's say, 10 meters per second. So I've taken hypothetical values just to simplify the calculations as far as possible. And in this particular situation, the astronaut is having a tool. So the astronaut is holding the tool in the hand. So this is a before case. Let me write. So before the tool was thrown by the astronauts, this is how the setup looked. And let's say the mass of the tool also we assume as 1 kilogram, just for the sake of simplicity. Now let us analyze the after case. After the tool is thrown away by the astronaut. So let's draw. The astronaut will still be moving with, let's say, a reduced speed of 9 meters per second. So let's say the tool has been thrown forward. So the astronaut will be moving with a slower speed. On the other hand, the tool, since it is thrown ahead, let's say it travels with a speed of v. So v is the speed of the tool afterwards. And how do we figure out the value of that v? We just use the law of conservation of momentum. Initial momentum should be equal to the final momentum. So in the before case, let's write pb, which is the before momentum, should be equal to after momentum. Initially, the astronaut and the tool both were moving with a speed of 10 meter per second. So we can write total momentum is 1 into 10 plus 1 into 10. Afterwards, the astronaut is moving with 9 meters per second, and the tool, on the other hand, is moving with a speed of v. Now let's simplify this. We'll get 20 is equal to 9 plus v. And if we make v as the subject, we will get v as 11 meters per second. And now let us analyze the kinetic energy. So initial kinetic energy of the astronaut will be half mv squared, so half into 1 into 10 squared, plus the tool is also having the same kinetic energy. So if we simplify this, we should get 100 joules as the answer. So initial kinetic energy of the astronaut plus the tool is 100 joules. Afterwards, the astronaut was moving with a speed of 9 meters per second. So let us write down the final kinetic energy of the astronaut will be half into 1 into 9 squared, plus then we have the tool, which is half into 1 into speed of the tool we had figured out was 11 square. So let's try to simplify this. We will get 9 square divided by 2 plus 11 square by 2. If we simplify this, we'll get 81 plus 121 by 2. And if we simplify, we will get 101 joules. So initial kinetic energy was 100. Finally, it was 101. Hence, we can say kinetic energy actually increases. So please remember this as a rule. In questions like this, total kinetic energy of the entire system will increase, but the momentum does not change. Hence, the answer is option D. But in an exam scenario, solving so much, doing all these calculations might feel tedious. So that's why in an exam situation, what we should do is going back to the question, it is saying an astronaut is moving at a constant velocity. Now, the question has not clearly specified how much is the velocity, so we can assume that the velocity is zero. And then that will be very easy to get to the answers. How do we do that? We have an astronaut holding the tool at rest. So let's try to draw this. So this is an alternate approach which we are considering. So we have an astronaut plus the tool initially stationary. So momentum is zero. Afterwards, momentum, of course, should be zero. So this is the before case. Afterwards, what is going to happen? Let's say the astronaut throws the tool forward. So let's draw the figure. So we have the tool which has gone forward with some speed, let's say v1, and then because of the law of conservation of momentum, the person will have to go back. This is similar to once a bullet comes out of the gun has a tendency to recoil backwards. That's why once the astronaut throws the tool forward, the person will go backwards. Let's say the speed is v2. So now we can very simply analyze initial kinetic energy of the system. We can say it is zero because the astronaut and the tool were stationary initially. Afterwards, we have non-zero velocities v1 and v2, which means kinetic energy is definitely not zero. Hence, we can deduce that kinetic energy has actually increased. So, this is the ideal and the fastest way to prove that the kinetic energy in this situation will have to increase, whereas the momentum doesn't change.